Hello, everyone. Welcome to a Q&A about science and technology for kids and others. Let me see. I have a number of questions saved up here. I just want to say that I'm happy to try and explain things at all levels, um, from although the very technical ones uh, I might skip here. Let me see. Um, ZT asks, if everything was super condensed at the beginning of the Big Bang, why do you think everything did not just become one single big black hole? Okay, that's a complicated question. Let me see what I can do to explain that. The fundamental answer to that question is because at the beginning of the universe, the sort of the thing in the traditional view of cosmology that sort of began the universe was this big outward push. And the what forms a black hole is things falling in as a result of the force of gravity. So in a sense, the Big Bang at the very beginning of the universe was like a giant explosion that pushed things out. Whereas what you need to form a black hole is something where gravity has sort of taken over and everything is being crushed together by the force of gravity. Now let's try and unpack that a bit. The the thing that sort of traditional physics starts from is kind of a mathematical setup for this thing called general relativity that Einstein invented in 1915. That's kind of the core theory of how gravity works and how space-time is built. That has been the traditional theory of physics for the last 100 or so years. In very recent times, with our physics project, there's sort of a different more lower level theory of how space and time are formed and so on. Instead of the idea being there's just this continuum of space that's described by that has coordinates that describe where you are in it and so on. Instead of that continuum of space, in our model, space is made of something. Space is made of this giant network of atoms of space. The atoms of space are these featureless elements whose only characteristic is that they have relations to each other. Those relations can be represented by a network. So in our model of physics, sort of everything in the universe is made of space, but space has the structure. And the particular details of that structure correspond to the particles, the electrons, and so on, or things like black holes for that matter. But that's not the traditional view of physics. That I think it's the correct view of physics. It's kind of a lower level view of physics than the traditional view, which talks about this kind of continuum of space-time. It's kind of like you could be talking about a fluid like water at the level of just saying, well, it flows this way and has little eddies in it and so on. Or you could say, what's really underneath? Well, it's a bunch of molecules bouncing around underneath. And that's the same as sort of the relationship between the traditional view of space-time and traditional physics for the last 100 years or so and our view in our physics project. Okay, let's talk about the traditional view first. So the traditional view is a bit abstract. It really says there are these equations, the so-called Einstein equations, that describe abstractly kind of the curvature of space. They describe this continuous thing that represents space. It's like, well, what really is that? Is it something where the sort of the points in space are sort of related to each other, are kind of have distances that correspond to what they would be in ordinary flat space, like something that's just laid out on a plane or the three-dimensional analog of that? Or do they correspond to things that are in some kind of curved space, like the way that you could find distances on the surface of a sphere? In the actuality of our universe, we're dealing with three-dimensional space, but it's three-dimensional curved space, just like the two-dimensional space that will be the surface of a sphere. It's two-dimensional, but it's curved because it's on the surface of a sphere. And so that curvature leads to different distance relationships. For example, if you say, well, I'm going to go as far as I can. If you were just on a plane, just keep going, potentially an infinite distance. But on a sphere, after you keep going, keep going, keep going, eventually you'll come back to where you started from. So Okay, that's sort of the framework for describing things in traditional general relativity. So how does one describe the beginning of the universe? Really, by fiat, one just says the universe has this parameter that is an expansion rate. And you say, and for whatever reason, and we don't say what the reason was, the universe just was set up to start expanding. And then what happens is the universe is still expanding. And we can tell that because we can see that galaxies are getting further away from us. Not the, we It's not the case that everything in the universe is expanding. We are not expanding, but the distances between distant galaxies are expanding. What's happening is things that are held together by forces like the forces between atoms and so on, they just stay at the size that they stay at. But things that are very far apart, there's a little tug of pulling things apart that really is just that parameter that is describing the structure of space-time as it's been sort of inserted into the standard model of cosmology. And there's this little, it's usually called the Hubble flow after Edwin Hubble, who discovered experimentally the expansion of the universe in the 1920s. Um, and the Hubble flow is kind of just this tendency of things to get pulled further apart. If that tendency is resisted by other forces, well, then the things just don't get further apart. Now, in the way the universe has evolved, it is a big question whether the universe, which got this push at the beginning, is it eventually going to, through gravity, just get pulled back together so that eventually the universe, after it's expanded for a long time, maybe for 100 billion years, eventually will sort of turn around and start contracting again. And then what started as a big bang will end up in a big crunch. Well, that's in the traditional view of cosmology, it's really just a parameter, whether the universe expands forever, eventually has a big crunch or whatever. Now, if the universe got a certain push at the beginning, one way in which it can be sort of prevented from expanding as much is if there's so much material in the universe that produces gravity that the sort of pieces of the universe are pulled together by that force of gravity. And there's sort of a question of what's in the universe. There's a certain amount of luminous matter that we can see in the universe, the 100 billion galaxies that we can observe in the universe, and so on. But there's pretty good evidence that it is as if there is 10 times as much of something else than there is of the material that we can see in the universe. And the traditional view of that is that the 10 times as much stuff that we can't see is, quotes, dark matter. I happen to think that imagining that it is a form of matter is probably wrong. It's rather a feature of the way that gravity works. But let's put that aside for a second and just say that in sort of the traditional view of physics, what one has to do is to say, well, in addition to all the matter we can see, there's this dark matter that we can't see that's pulling things together, that's resisting the expansion of the universe and making the universe start collapsing again. Well, that was sort of an idea for a while that it's kind of dark matter was the main thing in addition to the matter that we can see. But then there were some anomalies found. It's not completely clear they're experimentally correct, that actually the universe was getting sort of accelerating a bit in its expansion rather than slowing down. If you have matter that has mass, it will pull things back together and make the expansion slow down. But it seemed like, well, the expansion was actually accelerating a bit. How could that be? So then an additional thing, I won't say kludge, but I might, was introduced, the idea of dark energy. Dark energy is essentially matter with negative mass. It's something with negative mass. And when you have positive mass, gravity, the force of gravity sort of pulls things together. But if the mass of a thing was negative, gravity would be a repulsive force. It would push things apart. And so the idea of dark energy is to have something in the universe which pushes things apart a bit. Now, I would say that the things haven't really landed in terms of how much dark matter, how much dark energy does there appear to be. But we're actually pretty close to a situation where the expansion of the universe is such that we're expanding and it's sort of slowing down, and eventually it's just coasting. The expansion is neither speeding up nor slowing down. That seems to be pretty close to what the actuality of the universe. If the expansion was sort of reversed and the universe went into a big crunch, it's kind of like the universe becoming a black hole. It's like, but it isn't mathematically quite the same as a black hole because a black hole is a thing that happens within the universe, within space, as within sort of an outside version of space. There's this still piece of space that gets crushed, turned into a black hole. That's a little different when one's talking about the whole universe, but it's a similar kind of general phenomenon. If the universe kind of contracts again and has this big crunch, it's kind of like the universe forming a black hole, except that with a black hole, most of what you experience in a black hole is from outside the black hole. Whereas in that description, it's like you're inside the black hole. Well, in fact, the original expansion of the universe can be thought about as being a little bit like a white hole. In a black hole, the idea is that you have all kinds of matter and a star and whatever else, and the force of gravity is pulling things together so strongly that eventually nothing can withstand that, and the thing is sort of crushed into this thing which becomes this kind of anomaly in space-time. Well, you can imagine reversing time in that picture and saying instead of everything getting crushed and ending up in a black hole, that actually it could be the opposite way around, and everything that was, and you could instead be spewing matter out instead of having matter collapse into the black hole. Now, actually getting such a thing in the universe, it's not clear how that would happen, although it is the case that to a very close approximation, the laws of physics appear to be, and for these purposes, it's thought to be exactly true, the laws of physics are kind of reversible in the sense that if you see a process happening kind of like two balls colliding, they could as well collide and bounce off that way as they could collide the other way and bounce off the original way they came. So at that level, sort of things in physics are reversible. So if there are black holes, you might say, why aren't there white holes as well? That's an interesting issue, and it relates to ideas about the second law of thermodynamics, the kind of arrow of time. We can talk about that separately. But the way that it is, it's kind of like most of the time, there are no white holes, so it seems, with one exception in the usual theory of physics and cosmology, that the origin of our universe was sort of like a white hole. It's sort of things were kind of spewing out of things were being sort of created at the beginning of the universe. Well, so a question, let's see. The very beginning of the universe, the universe in the traditional view of physics started as this tiny thing where kind of the whole mass of the universe was concentrated in this tiny kind of thing that seems like sort of it's so intense that it's like a singularity in space-time, just like the kind of singularity in space-time that happens inside a black hole. So, but it's more like a white hole where that singularity in space-time is spewing out everything that exists in the universe. And at the very beginning of the universe, yes, everything was very, very small. The whole mass of the universe was concentrated in this tiny region. But as I say, as a matter of sort of the mathematics of what was going on, there was this parameter that was expansion rate that said, well, actually, it's this giant explosion that everything is being forced outwards. So let's see. I mean, the mathematics of what's going on is once you get over the sort of level of understanding tensor analysis and various kinds of things like this, the mathematics is sort of straightforward to write down. Why it works that way, nobody can say. Let me explain a little bit about the idea of singularities in space-time. So I mentioned that in a traditional view of physics, space is this kind of continuous thing where you can like put things anywhere you want in space. Well, it all works fine until you actually study the kind of what happens in the universe when there's lots of mass in places in the universe. The presence of mass causes curvature in the structure of space. And when there's too much mass, there's sort of too much curvature, and eventually you get a so-called space-time singularity. What is a space-time singularity? Well, It's a place where essentially the the curvature of space goes to infinity. What does that mean? It means we've got these equations which are talking about the value of the curvature of space, but the equations basically are saying the curvature of space goes to infinity, which means the equations don't apply, at least right at the point where the curvature of space is infinity. So it's a very weird situation. And in traditional view of general relativity and traditional view of space-time, the way one thinks about it is the equations of space-time apply almost everywhere, except there's a little hole punched out of the universe where we can't say anything about what equations there are or what might be going on. That's what happens in a space-time singularity, is you have to think about it as being kind of a hole punched out of the structure of space. It's kind of kludgy. And that same kind of idea about sort of a hole punched out of the structure of space is the kind of thing that one sort of thinks about at the beginning of the universe as well. That's the thing that happens at the very center of a black hole is this, this notion of a singularity in space-time that's kind of like a hole punched out of the structure of space. The way black holes work, they have a so-called event horizon, which is something that is far outside of that singularity at the center. Um, and it is the place where things can things, if anything passes up through the event horizon, it can go into the black hole, but it can never escape from the black hole. It's even light going at the speed of light can't go fast enough to escape the pull of gravity for the black hole. And that phenomenon happens at the event horizon. In other words, if you're a photon trying to make it out of a black hole, you kind of turn around before you get to the event horizon. And if you're a spaceship kind of falling into the event horizon, actually to you falling in, you don't really notice much happening. But to anybody on the outside, kind of you would actually seem to, you look as if you're frozen at the event horizon to somebody far away from the black hole. But but what would happen is you will no longer be able to communicate to the outside world. Any radio signal you send will be kind of turned around and pulled back into the gravity of the black hole. Now, the picture of how a black hole might form in the universe as the universe is today is, oh, you've got all this matter, you've got this star that's a very massive star and it collapses, and all that matter is producing mass that's going to form this black hole, and where eventually the singularity forms at the center of the black hole, an event horizon forms around it, and so on. Well, that's a good picture, and that's probably how black holes form in the universe as the universe is today, and so on. But in the mathematics of it, it's much weirder than that. The mathematics, all that matter that we said fell into the black hole, it doesn't matter, so to speak. There is a solution to the equations of general relativity that is just a singularity at the center, an event horizon around it, no matter at all. It's a vacuum solution to the Einstein equations, except for one little footnote, which is that there's a hole punched out of space at the center of the solution. And so it's as if a black hole could perfectly well just be sort of a pure blob of gravity, with the one exception that there's this hole in space that just is a place where the equations that describe what happens with gravity just have nothing to say. So it's a bit of a weird and arguably somewhat kludgy situation. And that's the kind of the picture of how the early universe starts is a picture quite similar to that, where you're starting from this singularity in space-time at the beginning of the universe. And then, as I say, it's as if you're sort of the inside of a white hole with this expansion that was just sort of forced upon you. Well, it's a bit different in our model of physics. In our model of physics, space has a structure, and the idea that there would be sort of an infinitesimally small hole punched out of space, that doesn't make any sense. Instead, what happens in a black hole is that in our models, this structure that represents space, this network that represents space, where the actual space in the universe has an immense number of nodes in this network. The network, the scale of the network is absolutely microscopic, unbelievably far below anything that we've been able to detect to date. Of course, it's an interesting question where there might be phenomena in the universe that kind of act like magnifying glasses to kind of like gravitational microscopes to be able to sort of see down to the length scales that are of the order of the actual elementary length in this network. But that's a separate issue. When it comes to sort of the general structure of space, it's this network, very small scale. And when you form a black hole, it's a feature of the structure of this network. And actually, the way the network is set up, the progress of time is the progressive updating of this network. The network is continually rearranging itself just locally, and that's what's happening. That is the progress of time in the universe, in our models. In a black hole, at least the simplest case, the sort of the big thing that happens is those rules that update the network, there'll be a place where those rules just don't have anything to say. The structure of the network is such that those rules just don't apply. So the network just doesn't get updated there. That corresponds to a place where effectively time is stopping. That is the nature of the kind of space-time singularity that exists, at least in the simplest kinds of black holes. So in our models, what was kind of this somewhat kludge of this sort of hole punched out of the structure of space becomes just yet another feature of this network that represents the structure of space. But it's a place in that network where most of the network is being updated, but time is passing. But just in at least one place in the network, it's stuck. Time doesn't pass. And that's the thing that corresponds to the singularity at the center of a black hole. And you get in our models the analogs of the event horizon. You get this kind of idea that there are causal effects which can move from the outside to the inside of the event horizon, but not the other way around. So that's kind of how a black hole works in our models. What about the beginning of the universe? Well, in our models, kind of the idea is there's this network, it's continually getting rewritten, the network can get bigger and bigger. What is the beginning of the universe like? Well, the beginning of the universe is potentially you're just starting from a very tiny network, and then the network is progressively growing. Now, that is very analogous to this sort of singularity because time, if you say, well, what happens before the universe? Well, there was just, you could say, in this picture, we're going to go a little bit deeper in the rabbit hole in a minute, but at this level, one could say, well, there was this network, and it just was there, and it was a thing that existed, and well, had any time passed? Well, the measure of the passing of time is the updating of the network. So if there's just a network there, there's no notion of how long was it there, because the measure of time passing is the updating of the network. And so it doesn't really make sense to ask what was there before the beginning of the universe, because once there is a network, whenever it updates, that corresponds to sort of a tick in the progress of time. So it could be the case that from sort of an outside the universe view, which we don't think we can get, if we could have an outside the universe view, one would say, oh my gosh, what's that universe doing with itself? It's just sitting there for most of eternity, not doing anything. Oh, suddenly it's starting to rewrite itself. Ticks are happening. But to an observer inside that universe, the only thing they know about is when the updating happens, because their own sort of internal clock, there's their own clock of experience, is based on the same thing that the clock of the universe is based on. So it's to the observer in that universe, it's as if all they see is time once time is running, so to speak. So, but the picture of what things look like at the very beginning of the universe, if you have this tiny network, one feature of a tiny network is that the sort of distance between different nodes in the network, if you're just going across edges in the network, is always very small. So it's as if every node in the network is kind of connected to every other node, which is kind of what you would get if you had an infinite dimensional space. Normally, if you have kind of something like three-dimensional space, let's say you have a grid in three-dimensional space. If you start from a point in the grid and you say, well, how many grid points are there sort of right next to that. You can go down the coordinate axes. There'll be an x coordinate, a y coordinate, a z coordinate. You'd say there are, plus minus x, plus minus y, plus minus z. So there'd be 6 points that are sort of a distance 1 on the grid away from where you started. You go distance 2 away. You keep going. You're kind of filling in the volume of a sphere, which will be proportional to the distance you go cubed. And in general, as you think about sort of something which is just a grid where you don't have everything connected to everything, you just have things kind of going in their coordinate directions. If it's a three-dimensional grid, the number of things will go like r cubed and so on. But if you have this network that's perhaps a very tiny network where kind of everything is connected to everything, it's as if it's kind of like you say, well, where do you get to from this point? Well, you almost immediately get to every other point. It's like it's an infinite dimensional thing. It's kind of like r to the infinity is the function that gives how many things you get to after you go r steps. So in our picture, the very beginning of the universe is like an infinite dimensional thing where everything is very close to everything. And only as the universe expands does it become something which, for reasons we don't know why it's 3, but it ends up with a limited dimensional kind of thing that is what we now perceive. Okay, so just to go to the very deepest point in the rabbit hole, the deepest point in the rabbit hole is the thing I call the Roolead, which is kind of the thing that is sort of underneath sort of the description of the universe that I was just giving. In the description of the universe that I was just giving, I said, well, you have this network that starts at this little network, and then it applies this rule, and that rule causes it to sort of keep sort of growing out the universe as we experience the universe. But the immediate question you'd ask is, well, why did our universe get that particular rule and that particular initial network? Why wasn't it another one? Is there something special? Is there sort of a creator of the universe who picked, hey, you guys are going to get this network as your initial network and this rule? Is that how it worked? Is there arbitrariness in the structure of our universe embodied in that initial network and the rule that's being used? Well, I think the answer is there isn't. And the reason is that really what's happening is that all possible rules and all possible initial networks are being used. And what is the case is that our experience is just a tiny slice of that whole kind of structure of all possibilities. We exist in a particular place, just like we exist in a particular place in space. We're on this particular planet, this particular galaxy, and so on. So also we exist at this particular point in what I call ruleal space, the space of all possible rules and so on. Our experience is based on being at a particular place in this collection of all possible rules and so on. But there is sort of this very, very integrated thing that is what you get by following all possible rules with all possible initial conditions and just seeing what is formed from sort of the entangled limit of that. It gets sort of entangled because two things that might be different states of this universe will end up happening to be the same state. And so you'd kind of merge them together if you were making kind of a graph of what happened. And so the idea is that the big sort of discovery of our physics project, I suppose, is that in this idea of the Roolead, which is sort of this necessary object that's this entangled limit of all these different processes, that observers who have the characteristics that we have necessarily perceive what's going on in the Roolead in a particular way, and in a way that reproduces the main laws of 20th century physics. So that's sort of the big fact there. But now, how does that relate to what happens in the very beginning of the universe? Well, the first thing to say about the beginning of the universe in our models is that nothing like us can exist there. The observer, like us, that now observes the universe, 14.5 billion years after it started, that the observer that's now capable of observing that just couldn't have existed in that very early moment in the universe. So to ask, what is the universe like? What are the laws of physics like in that very early moment is a weird thing to ask because the laws of physics that are relevant to us are the ones that we perceive. There are other laws of physics that some kind of alien could perceive with different sensory apparatus and all that kind of thing, different way of thinking about the universe. But the laws of physics that we perceive depend on what we are like as observers of the universe. And observers like us simply couldn't have existed at the very beginning of the universe. So we can't really say that our kind of we can't say sort of how we would perceive the laws of physics. Would we perceive something to be like gravity or something like that in the very early universe? Because there just isn't a way of looking at things in the uh, in the way that observers like us do. And it's kind of like an observer like us just doesn't fit in a tiny, very early universe. An observer like us needs the universe to be fairly calm so that we can sort of live out our lives without being sort of torn apart by changing structure of space-time and things like this. Of course, that depends on us being observers, kind of the size we are and the nature we are. You know, if we were galaxy spanning sized observers, the central black hole of our galaxy might cause us a lot of trouble, but it doesn't. It's irrelevant to our everyday lives, so to speak. We can be observing the laws of physics perfectly happily without ever thinking about the central black hole of our galaxy sucking up stars and doing all kinds of other things. So it's kind of the way that we perceive things depends on the nature that we have as observers, and questions about how we would perceive or attribute the laws of physics to the very early universe are sort of questions that aren't really defined for an observer like us. We can say at a more abstract level what is the structure of the universe at the beginning of the universe. And I will say that this whole question about what happens, sort of when is the beginning, what happens before the beginning, in the context of the Rulliad, none of that really makes sense. The Rulliad is this thing that is sort of this necessary abstract object, and it's a thing you can just abstractly define. There's no sense of whether it was created. It's no more created than, you know, the number one is created. The number one is something that sort of has an abstract existence, independent of whether you have one rock or whether you write a one symbol down on a piece of paper. And so similarly, that's true with the Rulliad also. The fact that the Rulliad feels to us like it has a reality is because we are observers who have this idea that we have an inner experience, and that's what leads us to sort of take what is ultimately in a sense, an abstract thing and sort of breathe reality into it. That's something that is a consequence of the fact that we are here as observers of the thing, having our sort of inner experience. Boy, this is getting very philosophical here. But just to say that the way that we can think about the Rulliad is the Rulliad is just this abstract thing. So you say, well, does it all just exist already? I mean, or is it being created through time? We can have different views of this. We can just say the Rulliad all exists abstractly, but we, as observers of the kind we are very slowly moving through it as we're slowly sort of discovering more of the Rulliad as we go through time, so to speak. That's one point of view. The other point of view is that we are kind of watching the creation of the Rulliad as we progress through time. These pictures are, in terms of what we perceive, are exactly equivalent. In terms of how one might abstractly think about them, they're sort of also rather equivalent. But you know, one of them one could sort of say from the outside the universe view, which is not a view we can ever get, they would look different. But that's not really relevant to think about what would it be like from outside the universe when there is no notion of outside the universe. But in any case, with respect to sort of the very beginning of the universe, it's the Rulliad sort of just is, and the sort of the passage of time happening really starts to be noticed when there are observers like us who can sort of tell either that they're moving through the Rulliad or the Rulliad is getting created as they watch it, so to speak. And so this idea of sort of, is there a moment where somebody pressed the go button type thing to have the universe happen? No, that's really not the way it works. It's just a thing that is, and at some point one might sort of start noticing it because one has an observer like us. Right, let's see. Perhaps some questions related to the kinds of things we were just talking about. Jason asks, is expansion of the universe real, or is our observation becoming more powerful and giving us an illusion of expansion? No, the expansion of the universe is real. How do we know? We know because we can see galaxies that are so-called redshifted with respect to us. What does this mean? So stars are, they do what they do. They fuse hydrogen atoms with other hydrogen atoms to produce energy and light and so on. Stars do what they do. And stars, in a first approximation, have always been doing what they do. Once you have a star, you kind of know what it does. That's not completely true because there are things that get produced, heavy elements, for example, get produced in the earlier universe and then used in later stars. But in a first good approximation, stars just do what they do. Whenever you've got a clump of matter that was pulled together and that started doing fusion of hydrogen, for example, and producing light, it'll be like a star. How big the star is, well, that affects what characteristics it has, but there's a range of sizes of stars, and stars just do what they do. Okay, so in particular, that means a star like the sun, which is kind of on the slightly larger end of stars, but there's a distribution of sizes of stars, but it's kind of a fairly typical star. It produces to us what seems like white light. That means it's a combination of sort of the whole rainbow of colors of photons, um, but it produces what we perceive as being roughly white light. The peak of its spectrum is right in that particular place. That sort of it's the place that's kind of the center of the combination of colors that makes white light. Okay. So now what happens when we have a star in a galaxy that's far, far away, so to speak? And where that galaxy is where the galaxy is moving away from us because of the expansion of the universe. Well, it's kind of like what happens when you hear a siren go by. When the siren is coming towards you, it's higher pitched. When it's going away from you, it's lower pitched. That's just a consequence of thinking about the waves that make the sound that corresponds to the siren. Those waves are the waves come to you at the speed of sound. They're a certain distance apart. But if the siren is moving towards you, the waves will be kind of bunched up and they'll be closer together. Them being closer together corresponds to you perceiving a higher pitch. When it's going away from you, they'll be further apart. You perceive a lower pitch. The details are different, but the same kind of thing happens with light. When you have something that's emitting light and it's traveling towards you, it will be blue shifted. There will be sort of a higher frequency of light that moves white light into the blue area. If it's going away from you, it'll be red shifted. The frequency of light goes down. It'll be shifted towards the red, and so on. So what happens? Well, what we can observe is that the galaxies that we're seeing are red shifted relative to us. I'm trying to remember what the largest redshift for a galaxy is. I think it's still maybe less than 5. So that means a redshift of 5 is pretty dramatic. It means that the color of light that you get from the stars, even though they're emitting, we assume the same color of light. The frequency of the light will be 1/5 the frequency that it would be if we were right there with the galaxy, because it's moving away from us. It's moving away from us so fast. It's moving away from us at a significant fraction of the speed of light. If the um, if the galaxy was moving away from us at completely at the speed of light, in a sense, it would be redshifted down to zero energy, but it isn't quite going that fast. Well, Actually, that's not quite the right way to say it. It's a more complicated story. It has to do with figuring out how light propagates in a curved expanding universe. Let's not go there for a second. But I'll just say that the um the fact that it's the galaxy is receding away from us is something we can absolutely measure by measuring the frequency of the light that comes from it. And the furthest we can get is what is a redshift of I think 1500, which is takes us down from the kind of star surface temperature type temperatures down to the temperature of the cosmic microwave background, 2.7 degrees above centigrade above absolute zero, 2.7 kelvins. Um, and what happened there is that at the beginning of the universe, during the sort of very early stage of the universe was incredibly hot, and the uh, in fact, it was so hot that every atom had been sort of torn apart. The atoms hadn't formed yet. They were just separate electrons and protons and so on. About 100,000 years after the beginning of the universe expanded and cooled down enough that atoms could actually form, that protons and electrons could get bound together and make hydrogen atoms. At that point, one of the things that happened is that the universe became transparent to light. Before that time, it was kind of like a flame, a plasma, where you kind of can't see through the thing. It's just sort of separate electrons and protons and so on, and it has light can't get through it. But 100,000 years after the beginning of the universe, the electrons and protons combine. It's often called recombination. It should really be called combination because it's the first time it happened in the history of our universe. That combined to form hydrogen atoms, at which point the universe became transparent. And what we're seeing in the cosmic microwave background in every direction in space, we see back to that initial hot gas that was in that plasma that was in the early universe. We see back to 100,000 years after the beginning of the universe, but it is very redshifted. It's redshifted to the point where even though it was kind of star surface temperature like temperatures, it is now shifted down to being 2.7 degrees above absolute zero. So that's kind of the story of that. And it becomes the whole question of figuring out the expansion rate of the universe and so on. It's a tricky question. And what uh, there are there are all kinds of issues about sort of whether you can tell how far away things are without knowing their redshift. How do you independently tell how far away something is? Well, you can tell it if you say, well, this galaxy with all its 100 billion stars or whatever it is should be this bright. And actually, what we see is light of this intensity. Then you can use that to try and figure out how far away the galaxy is. That's a fine idea, so long as the galaxies very early in the history of the universe really worked the same way as galaxies today do. And they probably didn't work exactly the same way. Just like in our galaxy, there are heavy elements. Well, you get hydrogen and helium in most stars, but only in some limited set of stars that have exploded into supernovas and so on, and a few other cases do you get the heavy elements like, I don't know, lead or gold or something like this. And those things there will be an early population of stars that produce those things, and those things can then be used in later stars. And there's similar kinds of phenomena, presumably, for galaxies. And so it's harder to tell sort of what the absolute intensity of a galaxy is, the absolute intensity of all the light produced by a very early galaxy is. And there's been lots of argument in the world of cosmology about sort of the so-called standard candle of, what's the thing whose intensity is exactly this intensity throughout the history of the universe. Let's see. There's a question here from Jay Mura. What is the universe expanding into? Yeah, well, this is where the sort of intuitive picture of sort of things expanding kind of doesn't really hold up. And the sort of the description that one gets in traditional physics is really this mathematical description, and one's just sort of intuitively saying, oh, it corresponds to expansion. The real answer is that think about if you were on the surface of a sphere and the sphere was it was like a balloon and it was being inflated more and more. Well, your universe is expanding. The amount of distance between things on that surface of the sphere is getting larger, but it's not that surface isn't really expanding into anything. It's just getting larger. That's kind of a lame thing to say, but that's kind of the way that the mathematics works in describing the structure of space. In our models of physics, it's a little bit more explicit because what's happening is that this network that represents space and everything in it is just getting bigger. There are more nodes in this network, but this network represents everything that there is in the universe. So the question of what it's expanding into doesn't really make any sense. The universe just is this network. And however big the network is, that's how big the universe is. There's no ambient thing. There's nothing that the network is inside of. It is just that is the thing that exists. It's kind of like saying, like talking about, I don't know, something like numbers, some abstract kind of thing. It's not the case that you say, well, if I count to 1 billion, what's 1,000,000,001 made of? That doesn't really make sense. It's not the kind of thing you ask. There is 1,000,000,001. And so it is with the kind of expansion of the universe that you are creating this structure that is an abstract structure at some level, and you can add to it as a more abstract structure. We perceive it as the reality of the universe that's expanding, but there's no sense in which there is sort of a thing you can look outside of and kind of see it expanding into something else. Let's see. Peter says, my teacher said math describes the universe, but why is the universe so mathematical in the first place? Ah, yes, this is a complicated question. So one question is, what is math? And math, as we humans have practiced it, kind of originated maybe 4,000 years ago or something. People were talking about, I'm buying and selling this thing, I'm doing arithmetic, I'm counting money, I'm counting the weight of things or whatever else. That's one sort of origination of math, is the kind of doing of things like arithmetic. Another origination of math is I'm measuring out the area of my plot of land. I'm going to do geometry. And so mathematics, as humans have practiced it, is kind of the result of sort of thinking about those abstractions, about numbers and space, and numbers and kind of geometrical kinds of distances and so on. Well, that's what math, as far as humans practice it, typically is. Yes, there's a lot of overlays on that. There's algebra, there's calculus, there's all kinds of abstract mathematical ideas, but there's sort of the generalizations of those basic ways of describing things. So the question would be, why is it that those things that were invented for commerce or for land surveying describe the universe? Well, you could say, well, land surveying was invented to describe space as we perceive it. You could say, well, it's arithmetic was invented because we have, sheep and we were counting sheep or something like this. So in a sense, you could say, well, arithmetic and geometry were created to describe the universe as we perceive the universe. But they were really created, I think, in a sense, well, partly for that, but partly for sort of very practical, leading life kinds of purposes. So why should it be that they describe the universe? The Babylonians noticed that they could use arithmetic to be able to predict things about the motion of planets. And it's surprising that that would work. As things went forward in the history of mathematics and science, it was constant surprise that things that had been abstractly invented in mathematics were useful to describe the physical universe. Why did this happen? I think the number one reason it happens is because the features of the universe that we care about and notice are features of the universe that align with ones that we can describe with mathematics. The mathematics that we invented we invented it because it's the kind of thing that we can imagine and think about. But we also are extracting the laws of physics by looking at the aspects of the universe that we notice and care about. In other words, there are many things about the universe, about its very microscopic structure, features that we don't even have ways to talk about, that that we could be talking about, but we're not. Those are not what we make. That's not what we study in physical science, for example. We study in physical science those things that we can perceive. Now, when people in the past were doing physical science, they would say, well, we can study these balls bouncing around, but ask me about the beginning of the universe. I'm not even going to talk about that because it's not something I'm even close to being able to perceive. I don't have the telescopes to measure it, all those kinds of things. Similarly, if you're thinking about sort of the small, if you don't have the wherewithal to measure the very tiny things that are going on, you're like, well, I'm going to concentrate my science, my physics on things that I can actually perceive, not things I can't perceive. And so those things that we can perceive have turned out in many cases to align with the mathematics that we do. That's probably not a coincidence. It's probably not that the mathematics is it's the case that both the mathematics and the things we perceive are we're picking versions of mathematics, versions of physics that are ones that align with the way we perceive things. Okay, so how could it be different? Well, in mathematics, there are many possible mathematicses. We've just picked particular ones that seem to be useful. For example, we talk about numbers. We go 1, 2, 3, 4, 5, we just go a sequence of numbers, but we can imagine systems of numbers that don't work that way at all. Systems of numbers that don't form a single line of one number, then the next, then the next, then the next, but form some complicated network of succession of numbers that aren't, in a pure sequence like that, but do something much more complicated. There are things a bit like that are studied in abstract mathematics, but there's a vast universe of possibilities out there of things that have never been considered to be mathematics that we should study. The way we can think about this is in terms of axiom systems. We are asserting certain things to be true, and then we are deducing things from them. So, for example, if we're doing arithmetic, we have the fact that for any numbers x and y, x plus y is equal to y plus x. It didn't have to be that way. That is part of our definition of numbers and plus and so on. But we can take that as an axiom and we can build up its consequences, and that's part of what gives us the structure of arithmetic and so on. But we could pick a different axiom. We could say, x plus y is equal to y minus x minus 3 or something. And then we'd get a different kind of thing than arithmetic. And so there's an infinite collection of these possible axiom systems. We have chosen to study particular ones in mathematics. Many of those axiom systems, we can ask, how do they relate to our physical universe? They probably don't. But, we've picked the things we notice in the physical universe, the things we choose to make physical laws about, and we've also picked the things we choose to make essentially mathematical laws, axioms about. And there's an alignment between those two things. And that, I think, is the main reason that we feel that there is such effectiveness of mathematics in describing the physical world, because we're describing the aspects of the physical world that we notice and care about, and those align with the things that we've noticed and cared about in mathematics. So, for example, one of the things that I've done a lot of is studying arbitrary sets of rules, not the kinds of rules that we attribute to the universe, not the kinds of rules we study in mathematics, but just like have your computer pick a rule at random and see what its consequences are. That's the study of what I call ruleology, kind of exploring the abstract space of possible rules. Most of those rules neither make human mathematics, nor do they make the kind of thing that we perceived in physics in the universe. But those rules are perfectly good rules. You can study them and they have lots of richness in what they do, but they just don't align with our physics or our mathematics. And it could be the case that the aliens, so to speak, could be sensing aspects of the universe that align with one of these other kinds of rules that just is nowhere near the kinds of rules that we've studied in human mathematics. So needless to say, this is a slightly more complicated answer than uh, than one might expect. In other words, does math describe the universe? Well, no, not really. It describes the universe as we perceive the universe. It is a good way of formulating physical laws that correspond to the laws that we perceive for the universe. But those are not all possible laws, and they're not all possible forms of description. I mean, there's a long history to this idea that mathematics describes the universe, and it's been kind of a funny situation because on the one hand, as sort of a kind of a confirmation bias of a sort, because sometimes mathematics has been invented, and then people say, "Oh my gosh, this mathematics that was invented 50 years ago, it's a perfect fit to describe this aspect of the universe." And so that kind of makes one think, "Oh, there's just the mathematics that's out there. It's going to all fit in and describe the universe." But there's also quite a lot of mathematics that's never been found useful in describing the universe. And there's quite a lot of the universe that we've never been able to really corral into something we can describe mathematically. And in fact, in a sense, what we've tried to do with our physics project is to introduce something that is very different from traditional mathematics, but which is a way to describe the universe. So, for example, a big project that we have right now is what I'm calling infrageometry, the attempt to kind of build up a version of geometry that starts not from space as it is usually conceived, but instead from this hypergraph, this graph of atoms of space and so on. What is the thing that is like geometry that might have been invented as a piece of mathematics by the Babylonians, maybe, but wasn't? But that is the piece of mathematics in quotes, because it isn't mathematics yet in a sense, the piece of mathematics that we think actually describes the universe, but it wasn't pre-existing mathematics. Now, you could say, is it in fact mathematics? That's a good question. It's a question of what we mean by mathematics. It will be something that can be described computationally for sure. Is everything that can be described computationally mathematical? I don't think most people would say that that was the case. Mathematics is something where there's certain kinds of kind of global things you can say. It's not so much a question of, oh, you have this program, you run it, you see what it does. Mathematics tries to make more sweeping statements about things, these grand theorems that connect this to that. Those sweeping statements necessarily do not exist for many kinds of computational systems. That's a consequence of computational irreducibility, that there are many systems where you just have to run the thing and watch each step and see what happens. And so I think the thing that when we say is everything computational also mathematical, I don't think in any useful sense that's the case. I think that things which are computationally irreducible are not what one would usually call mathematical. Mathematical requires this kind of globality, this like I can wrap my arms around the whole thing. I can abstractly imagine the whole thing together. That's what tends to correspond to mathematics that humans have done, at least so far. And so I think when we just jump out into the computational universe, we're not really jumping out to things which are mathematical. Now, if by mathematics you choose to mean those things which are described by formal rules, then, well, you get all of computation too, but that's not what you would usually mean. And in fact, the particular formal rules that have been used in human mathematics are this very tiny set. You can, in my new kind of science book, I fitted them all on one page just to make the point that the set of possible abstract rules from which we build human mathematics is a tiny, very special set. Well, I don't know how special it is. It's the set that we happen to have chosen that correspond to things that we can perceive and so on. I don't think there's anything abstractly special about it. Let's see. Well, there's a question here, and this might get us into I'm going to do two things and then I should wrap up here. One is from Cynthia asking, if we talk about DNA as code, does that mean biology is basically computation? Maybe I shouldn't get too deep into this today. The answer is I think that the core, I've come to think, actually, particularly in the last year, that the core features of biology are deeply general features of computation. The details of how biology that we've got on this planet works, that's an arbitrary accident of history. But the general contours of how it works are very related to kind of fundamental, kind of general laws of computation, so to speak, and particularly this phenomenon of computational irreducibility. For example, the fact that biological evolution works, the fact that you can get sort of better organisms. Over the last couple of billion years, we've gotten more and more organisms that survive more and more and so on. The fact that that works, I think, is a consequence of computational irreducibility and its relationship to the kinds of fitness criteria that are used for organisms. This is kind of a long story, but I think that the sort of big contours of what happens in biology can be understood in terms of sort of the big contours of what happens in computation. But if you ask the specifics, why did we get RNA? Why did we get a particular kind of, I don't know, DNA repair mechanism or something? There won't be a theoretical answer to that. The basic answer will be, well, we were going to get something in general terms like that because of some general principle of computation. But the particulars came because of the particular kind of roll of the dice that led to the sequence of things that occurred in life on Earth. So there's, but this whole question about sort of how one imagines making a theory in biology is an interesting question. There's a lot in biology that sort of isn't, the details cannot be theoretical. The details are sort of arbitrary. It's like, can you make a theory of why we're on this particular planet? Well, no, it's just we happen to be on this particular planet. So similarly, can you make a theory of why some particular detail went the way it does in biology? No, you can't. Can you make a theory of sort of the overall arc of how these different things fit together in biology? I think one can, and something I'm actively working on actually right now. Let's see. Lucas asks, maybe this is our last question for today. Do you think kids can come up with new ideas that scientists haven't thought of yet? Absolutely. You know, one of the things about doing science is it's the most difficult thing in many ways in doing science is figuring out what questions to ask. Often, and it's increasingly true with all the kinds of computational tools I've built with modern AIs and so on, that once you know the question, you're off and running. You can try and get an answer. But really the thing that is the blocking step is figure out what the right question to ask is. You know, I mentioned biology in my attempts to make sort of a better theoretical biology. This particular thing that I'm thinking about, which kind of relates to, well, actually questions about sort of what is life. But what I know perfectly well is that I don't have yet quite the right question. Once I have the right question, I think I can nail it. But I don't have quite the right question. I don't have quite the right thing about sort of what's special about biological matter. What kind of special am I looking for? What you know, that's the thing is what question should you ask? Now, you know, sort of figuring out what question to ask, often there are questions one might ask that are really kind of obvious questions to ask, but the details of the development of some field of science kind of never really got to that question. They were on some different question. They built some huge tower. It's a very technical field. The textbooks are 1,000 pages long and so on. There's lots to learn. But by the way, that very obvious question from the beginning, it's like, well, everybody just whizzed right past that. Nobody asked it. And I think there are just many, many such questions and sort of the ideas around those questions that are just out there for the picking. And I think you know, what's interesting is that there are questions that are really obvious question to ask. And sometimes you can say, yep, that question was answered 500 years ago. We're done. And sometimes you say, oh, that question, that's an interesting question. I don't think anybody knows the answer to that question, even though it may be a seemingly quite obvious question. And I have to say, in doing these live streams, I run into this all the time. Like people ask different kinds of things, and some of them I'm like, yeah, like somebody was asking about the expansion of the universe. How do we know the universe is expanding? It's like, yeah, we really know that. That's in lots of physics textbooks. That's a really pretty nailed down thing. But when you're asking questions about, I don't know, the nature of time and so on, that what happens at the beginning of the universe, things like this, these are much more complicated questions where there's sort of things to say, but they're not clear that they're the things that are traditionally said, people just sort of avoid talking about it, and so on and so on. They're actually quite difficult questions based on existing knowledge. And so I think one of the things that is always fun with kids, and I hope there's some kids contributing questions here, is the questions you get are this full spectrum from ones where, yup, we've been knowing that for 500 years, to I know nobody in the world knows the answer to that question. And it's like if you don't know lots about science, it may be hard to distinguish which question is which, but you can absolutely come up with those questions. And kids, in my experience, do come up with those questions that span from well known to like, that's a good question. I never thought about that. I don't think anybody else ever thought about that. And I think it's particularly true when it comes to, there are kind of phenomena in everyday life. Some of those are questions that it's amazing nobody really asked. I mean, for a while, there was a whole bunch of physics being done about sand. And sort of any kid who made a sand castle will have sort of known things intuitively about the physics of sand, but those were not questions that had ever been asked in the sort of formal physics literature. They were kind of hard. They're now somewhat resolved, but that was something from not many decades ago that was sort of a frontier type of question that sort of any kid could start asking. And I think uh, there are many, many others of these. And as I say, if one's asking questions, one shouldn't get put off by the fact that somebody says, oh, yeah, that one's obvious. We've known that for 500 years. Because the next thing you ask, it might be like, nobody knows the answer. It is difficult often for people, particularly science teachers and so on, to deal with this because they know a certain set of things. And when somebody asks a question that they don't know the answer to, it's very hard for them to know, is it just that they don't know the answer or that no answer is known? I mean, I'm kind of spoiled because I've been involved in enough science and sort of enough connected to kind of the leading edge of lots of kinds of science that I really know, I can say with considerable certainty, just nobody knows the answer to that question because it's kind of like when people ask on these live streams, it's kind of always amusing for me to kind of try and remember, how do I know that thing? And sometimes the answer is, well, I learned it 50 years ago. And another time, the answer would be, well, I ran into the world expert on that thing about 3 months ago, and I asked them a question like this, and here's what they told me, type thing. And so it's really kind of the right from the kind of leading edge. But if you're not sort of connected to that, it's hard to know. And for example, for me, as I learn about new fields, there will be things that I kind of wonder, hey, I wonder how this works. And the answer might be, oh, it's in every textbook, or it might be nobody knows. I mean, as I've mentioned several times on these live streams, I've been trying to learn about economics. It's a very frustrating field to learn about because people will say, this is known. We absolutely know this, and this. You ask somebody else and they say, no, that's complete nonsense. There's no connection between this and that. And the people will say economics is all about scarcity of things. And other people will say, no, 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 completely not about that. That's irrelevant. Um, and people, partly in the case of economics, because it sort of segues into social questions and political questions, there's even more forcefulness in this is known, this is not known, et cetera, et cetera, et cetera. Do we know if we increase interest rates that this or that thing will happen to the economy? Maybe we know. Somebody will say we know for sure, and somebody else will say, well, that's complete nonsense. And it's a field where that's a particularly difficult one, I think, to be able to make a distinction between sort of the obvious and the unknown. But I think that that's one of the lovely things about science is that there's sort of a spectrum of things to think about, from ones where, yep, our civilization has nailed that one, we got it, we know how that works, to ones that are still, quite obvious questions to ask, but where we absolutely don't know the answer. And in my experience, kids are pretty good at asking, and I hope some folks here have been illustrating that, as you've asked many different kinds of questions over the course of the last 5 years or more that I've been doing these live streams about lots of kinds of things. Kind of, I hope, demonstrating. I don't know. I never know how many of you guys are kids and how many are ancient folks like me and so on. But in any case, I will say that I kind of would like to think that we've got some demonstration of the ability of kids to ask questions. Now, I think the question that was asked here would come up with new ideas that scientists haven't thought of. As I say, the key to that is asking new questions. And then the issue of, well, how does that actually work? Well, that's a complicated issue sometimes, but you're off and running once you've actually been able to sort of pose the right question. All right, I think I should wrap up here, but thank you for a whole bunch of interesting questions. One of the things that's happened over the last few years with these live streams is sometimes people will ask questions here that I certainly have never thought about, and I try and give you my attempt at a real-time answer to them. But then sometimes those have been seeds that have turned into things that I've really thought quite extensively about and have turned into things I've written and so on. And so I appreciate the kind of the poke for questions that I've never thought about before. All right. Well, thanks for joining me today, and look forward to chatting with you another time. Bye for now.